Okay. Okay. Hello, guys. This is the second video in the section 14.2 limits and continuity. Today, we're going to cover the definition and properties of the multivariate limit and continuity. I didn't mention this last time. So basically, calculus is a theory of investigating function. So the first property that we will be investigating about function is limit and continuity. That is what this section are for. And then we will have a deeper understanding of functions via its differentiability, integrability, and that will be covered in the next few sections and chapters, right? So the starting point now is the limit. So let us first again give the definition of the limit in a multivariate function, which is actually quite similar to the single variable function. So limit of a function f. So let me introduce the notation because I think I haven't used this before. Oh, maybe in the uh, section 12.5. Oh, yeah, 12.5 or 12 point. No, sorry, in 14.1. Sorry. Okay. So given a function f, this is a domain of f, and this is the codomain or the values of f. So in this case, I claim that D belongs to Rn, which is the n-dimensional Cartesian space. So you can think of n to be 1 or 2 or 3, which is the real line, the Cartesian plane, or the three-dimensional coordinate system we introduced in the chapter 12.1. So I just say it's D because not all functions are defined on every values of vectors. For example, you cannot define this function say this function whenever x plus y is negative, right? So I'm just saying that it is some function that is defined on a domain which is contained in the n-dimensional space, and we claim that this function has a limit at x equals to a. Note that I add a vector notation here, so this is a n-tuple, meaning that it looks like x1 to xn. You can think of it as xy or xyz. We say that the limit of f at the point A is L, this is value, if the following holds. So again, for every epsilon, a small threshold, we can choose a delta, which is another small threshold, so that whenever x and A is close enough, meaning that it is less than delta, then this guy is less than epsilon. So again, intuitively speaking, that is saying whenever x is close to A, then f of x is close to L, right? So you see that the difference between this and our previous definition is that I add a vector notation here because we're treating points in a n-dimensional space instead of a real line. And the distance we're using here is now the distance we define in, I would say it should be 12.1. That is the usual Euclidean distance, meaning that, for example, xy all the way to AB has distance to something like this guy with this guy taking square root. Okay, that's the distance that we're using. So for those 2 points, which are close enough, but it's not exactly that point, as we mentioned in the first video. We don't care about the point actually. We only care about the behavior near that point. Then we have f and L to be close enough. We can similarly define the continuity of multivariate function. Basically, a limit coincides with the function value. So if this function is defined at the point A, then and the limit of f of x is f of a, then we say that f is continuous at the point A. Okay, if you guys remember correctly, in the first video after those treatment, the first thing I do is to introduce you guys the right and the left limit, right? Because we can evaluate those directly, and then we can argue whether the limit exists or not by observing whether the left and the right limit exist or not, or even if they are the same. The difficulty in the multi-variable version is that the direction is more than two. So on a real line, the only way that you can approach a point is either from the right or from the left, right? However, for example, in the plane, in the n equals to 2 case, which is the two-dimensional space, if we want to approach, say, the origin, then you actually have infinitely many possible directions, right? You can approach it in different angles or in different strange paths, right? So we cannot define an analogy of right and left limit, which is why it is in general harder to find a limit in a multi-dimensional function, which things already is complicated when n is larger or equal to 2. So let us see how we can investigate this limit thingy. In an example that I'm going to present afterwards, there will be example that we're finding a limit. There will be example that we're disproving that the limit exists. And I will give a conclusion on what kind of algorithm you should apply when you believe that there is a limit or not. So let us do some example first. So first of all, this function is defined to be x squared minus y squared divided by x squared plus y squared. We want to ask whether the limit exists or not. So I would like to emphasize again that this function need not to be defined at origin, which is not defined, right? Because 0 divided by 0 is nonsense. We're only asking whether this function behaves nicely near the point 0, 0, the origin, okay? So we can try to do this. Instead of a two-variable case, let's consider a one-variable case. So let us approach the origin by a particular line, which is a straight line, given by y equals mx. So you can parameterize that line by tmt, right? T is any real number. So we see that if you plug this line into this function, you'll get t squared minus mt squared divided by t squared plus mt squared. However, t can be canceled out, right? So we see that a limit actually does not depend on t. It is simply 1 minus m squared divided by 1 plus m squared. What does that mean? That means that when you're approaching the origin in different direction, you get a different limit, which says that it actually has no limit in the origin. So this is like the case where the left and right limit exist, but they are not the same. So in this case, every direction gives you a different limit, meaning that you cannot have a nice local behavior near the origin. So the limit of f of x at 0, 0 does not exist, okay? As you can see, this right-hand side is a graph of this strange function. And you can see a limit is actually, the origins actually behave quite chaotically. So for example, if you go along this direction, you'll get something like here. If you go along this direction, you'll get something like here. If you go along the, this is the y direction, you'll get below the xy plane and you go below here. So every direction gives you different limit. So there is no general limit, actually a two-dimensional limit at the origin point. So that's an example where the function does not have a limit. And now let us present another example. Based on the previous example, you might wonder, so, okay, naturally, if every line going through the origin gives you the same limit, do you have a limit then? The answer is no, which is this example. So we see that in this example, you have x squared y divided by x4 plus y2. We are also interested in the limit at origin. So just to mention, the origin is nothing simple. The only reason that we consider the origin is because this function is actually nice anywhere else, right? Anywhere else, when the x and y are not both 0, it is well defined and it is actually continuous outside the origin. So the only possible problematic point is origin, which is why we are investigating that point. So as I mentioned, let us go through this limit via a particular curve, tmt. So if I plug in again into this function, it becomes a one-dimensional limit. So t squared, which is x squared, y becomes mt, and the denominator becomes t to the 4 plus mt squared, which gives us mt divided by t squared plus m squared, and let this 0. For provided that m is not 0, of course, because you cannot have 0 here. So we see that for every direction, instead of the y equal to 0, which is the x-axis, this guy is always having a limit 0. And also, if m is 0, then we're basically saying that y is 0, then this is just 0, right? So we know actually that so this is an notation here, along this line, y equals mx, when x y approach 0, we always have this being 0. However, this does not guarantee that the limit exists. Because other than the straight line, we actually have more ways to approach the origin. As I mentioned above, we can go like this, but we can also go in a straight way like this, and low straight direction might give you different limit or even not exist. So in this case, I choose a quadratic curve, t squared, which is following the path y equals x squared. So we're going through the origin like this, like that, and like that. So if you plot x to be t, y to be t squared, you will get t squared and t squared again, where the denominator becomes t to the 4 plus t to the 4. And that you can see the limit approaches half, which is not 0, that is calculated above. So even though the limit for approaching the origin in each direction of a straight line gives you 0, if you approach the direction of the quadratic curve, you get half, which does not behave the same as 0. So the limit does not exist. Okay. So to be precise, however many directions or paths that you check have the same limit, it does not really guarantee you anything. It only tells you that behave nicely along this particular curves because there are actually infinitely many different possible curves that can approach the origin or a particular point. So mostly we are just disproving that the limit does not exist at a point via choosing different paths that gives us different limit or non-existence of limit. Okay, we will conclude that afterwards. So now let us prove that the limit exists. Given this function f defined by x to the y4 and the denominator is x4 plus y4. So we want to ask whether the limit exists. So precisely, we will show that the limit actually exists and it's 0. So to prove the limit exists, we have to apply the epsilon delta definition. By fixing an arbitrary positive threshold, epsilon, we can choose delta to be epsilon, and then let us see what happens. So whenever the distance between x and y and the origin are less than delta, which practically means that the square root of x squared plus y squared is less than delta, then we show that the distance between the function and the potential limit value, which is 0, is actually just this function taking absolute value, right? If I factor out the x here, you get this times this. And this, regardless of what xy is always less or equal to 1, right? That does not depend on what x and y are. So this whole thing is less or equal to the absolute value of x, which is obviously less or equal to this guy. And by definition, by construction of delta, this guy is less than delta, which is epsilon. So everything boiled down, whenever the distance within x, y, and 0, 0 is less than delta, we always have the distance within this guy and 0 is less than epsilon. That means that we actually have the limit of f of xy being 0 by the definition of the limit at some point for a multivariable function, right? Okay, so one thing you might notice about this 3 example is that, first of all, why does the 2 example above here has no limit? In some sense, it is because that in this example, the denominator and the numerator have the same degree, right? It is of degree 2. So they kind of behave the same, meaning that you'll get a constant limit, which might vary along each direction. In this case, the numerator has degree 3 and the denominator has degree 4, which is the highest degree. So that means that the behavior of the numerator does not dominate the denominator when x and y approach 0. Because when x and y approach 0, this guy will be significantly smaller. So this guy will be significantly large. In some sense, this guy will actually blow up near the origin. And the reason why this guy has a limit 0 at origin is because that the numerator has degree 5 and the denominator has degree 4. So the numerator decays faster than the denominator, making it 0 at the origin. That kind of analysis is it's not really practical because that only works with this type of polynomial divided by polynomial t. But you can sort of guess the behavior of this kind of rational polynomial via analyzing the degree of the numerator and the denominator, as I mentioned. So let us conclude some principles of how you want to tackle these problems. So first of all, if you guess that the limit does exist for some particular function at some particular point, then the only way you can do that is applying the epsilon delta method, which is kind of hard because I know that epsilon delta proof is not really satisfying, and it actually needs a lot of practice. However, if you guess a limit does not exist, there's many ways to do that. So one way is to find a path toward the point that we are asking to show that a limit does not exist. Then we're done. That coincides to that's an analogy of the case in the one-dimensional limit that either the right or the left limit does not exist. And the second is to find two different paths so that the limit exists, but they are different. So that is an analogy of the right and the left limit exist in the one-dimensional case, but those two are not the same. So those are the two ways to prove that the limit does not exist. So as I mentioned, the epsilon delta method might be a little bit hard. So I will introduce another kind of method to tackle the two-dimensional limit. So this is the method that I'm proposing, the polar coordinate method. So we're actually stating that if a two-dimensional function satisfies this one-dimensional limit, so f of r cosine r sine theta goes to L whenever r goes to 0, and that the limit does not depend on theta. So basically what we're saying that r is the distance between the point and origin, right? So whenever a distance goes smaller and smaller and smaller, you get to a value which is independent of theta. So it does not depend on direction. So that practically just means that the limit of x, y, 0, 0 is L. Okay, those are the same thing. So this will be a good way to evaluate limit at the origin to translate everything into the polar coordinate. Oh, by the way, if you are not familiar with polar coordinate, please let me know. I would assume that you guys should know that because you should have covered that in calculus 1 or calculus 2. But if you need another separate lecture on that, I can do that. So please let me know. So those are the facts that we want to utilize. Let me present an example here. So we are calculating the limit of xy at the origin again by x cubed plus y cubed divided by x squared plus y squared. First of all, based on the analysis I just mentioned before, this guy should have a limit being 0 because the numerator decay faster than the denominator. It has a degree 3 in a numerator and degree 2 in a denominator. So let us prove this by polar coordinate. If we set xy to be r cosine r sine, then the numerator is simply r cubed cosine cubed plus r cubed sine cubed. However, the denominator is r squared cosine squared plus r squared sine squared, which is simply just r squared, right? That's kind of a definition of the radius. So you get this kind of notation. And then divided by r, you get r times the cube cosine cube sine. But it does not depend on theta, whether theta is, this guy is always 0 when r goes to 0, right? You can sort of argue that by perhaps the squeeze theorem. This guy is always less or equal to 2 and larger or equal to minus 2, right? And so you have minus 2r less or equal to this whole thing, and that's for 2r of this whole thing, which is both goes to 0 when r goes to 0. So the limit of this guy is 0, meaning that independent of theta, you have this guy. So the limit of this guy is simply 0. Actually, if you apply the same thing to, say, this case, oh, not this case, sorry, this one. So if you do this by something like r cosine r sine, then you will get a limit, which is, I think, cosine squared minus sine squared theta along y equals to mx. So you see that along the angle theta. So you see that this guy actually depends on theta, means that the limit along each direction is different, meaning that you don't have a limit at the origin in this case. So it is quite important that I mentioned here that this L is independent of theta. Okay, L is just a number, 2, 3, 0, minus 2, right? So again, let us try to conclude this. So now for you to compute a limit, there's two ways. One is epsilon delta method, whenever you can guess the limit is. Another way is to plug in your polar coordinate, which is only quite applicable in two-dimensional space. We will introduce another similar polar coordinate thingy in the three-dimensional space afterwards, but not today. Um, as if you want to disprove that the limit exists, then you would like to find either a path that the limit does not exist, which reducing to a single variable case, or you want to find two paths that they have the limit, but they don't have the same limit, right? So that's what we have done. And for the last remark, I want to mention that this kind of proof is not really important for our course. The only thing that you want to know is that multivariable function behaves really strange in comparison to the single variable function. So there's that. Next, we have the same arithmetic for limits as in the single variable case. It also respects addition, subtraction, multiplication, and division whenever the denominator is non-zero. So based on those arithmetic, you can sort of have this kind of class of continuous function. So it is very simple to show this three guys when y, z approach some point ABC, x approach A, y approach B, and z approach C. I would very much encourage you to try to show this by definition of limit, the absolute delta thing. It is very simple, and it might help you to have a better understanding of why that limit, why that definition works. So based on this, guys, and also this whole arithmetic, we know that we can multiply x, y, and z. We can add x, y, and z. We can subtract x, y, and z. We can divide x, y, and z. As long as the denominator is not zero, those guys will be continuous function. So, for example, this guy will be continuous if the denominator does not go to zero whenever x, y approach, say, 1, 2, 3. So in this case, it actually does not go to zero. And then this guy will be continuous function. You can do a direct substitution if you want to find a limit, which you get minus 11 divided by 8, right? So for now, we have a class of continuous function, which is polynomials, and rational polynomial, which is a quotient between two polynomials whenever the denominator is non-zero. How do we extend this kind of notation? Actually, this kind of class, how do we find more continuous function? So we will do that quite now. First of all, we have observed this back in the first portion of the video. We know that continuity is also nicely behaved under addition, subtraction, multiplication, and division. So that is the proof directly by definition. And we also have the squeeze theorem, which is actually the same as the previous one. We just mentioned the difference is just that we're considering a multi-dimensional variable now. So whenever these two guys squeezing f within a small neighborhood of x equals to a, then we still have the limit of f being L, provided those two limits are the same. Okay. As for the proof of this guy, which generalized the previous one-dimensional case, and also this guy, will be presented in the third portion. All right. And as we mentioned, we want to generalize the class of continuous function, right? So we want to show that, for example, tangent x plus y should be continuous in its domain, right? So that boils down to this proposition. We want to show that suppose f is a function, a multivariable function, goes to R, and G is a single variable function that satisfies these conditions. So the limit of f at A is C, the limit of G at C the limit of G at C is L. Now we claim that the limit of G circle F, the composition, at x equals to A is actually simply L. We have seen this before in the one-dimensional case where f and g are both single variable function, and we actually can generalize this to multi-dimensional version. So second is saying that whenever f is continuous at a point A and g is continuous at a point f of A, which is the limit of this guy, then g circle f will be a multivariable function that continuous at x equals to A. Where, as before, this directly follows from definition and this first item, right? So just to show the spirit, let us try to prove proposition 1 here. And as we mentioned, this is quite intuitive because Basically, this guy says that when x goes to a closely, then f goes to c closely. And this guy says that whenever y goes to c closely, then g goes to l closely. So when x goes to a closely, f looks like c, so g of f of x looks like L. That's the idea. So to be precise, let us do this. Again, we start with some epsilon larger than 0. That is a threshold that we want to eventually found at the end of the day. So by definition, there will be some delta larger than 0, so that whenever y and c are close enough, then g and l are close enough. After such delta, let us find another small threshold. This is eta, another Greek letter. So we find eta so that when x and a are close enough, so this should be a multi-dimensional distance. Let me use this notation. Whenever this happens, then f and c are quite similar. So by such definition, we see that whenever x and a are within 0 to eta, then by definition, f is of distance delta within c. And we can plug the y here to be f of x to see that since f and c are within the distance delta, so g of f of x and l are within a distance epsilon. So in conclusion, for this chosen epsilon, we can always choose some small eta so that whenever x and a are within distance eta, g of f of x are within epsilon distance of L. So that means that the limit of x to a of this function g circle f at x is simply L. All right? So that's again to demonstrate the power of epsilon delta definition. You can quantify anything. So why is this useful? As I mentioned before, we know that multivariate polynomials, say x squared plus y squared, x squared minus xyz, those are continuous functions, right? However, you cannot kind of generalize tangent, log, exponential, those things into multi-dimensional version. However, we can do a composition, right? For instance, we know that this guy's x squared, y squared, xy, 2x and sine y, those are all in itself continuous function. And now we can apply different one-dimensional function of that. So tangent itself in a one-dimensional version is continuous in this domain, right? So this is a multivariable continuous function. After applying tangent to that, which is a composition, then by our previous proposition, this is continuous in a multi-dimensional version, and so on and so forth. You can argue that for every function here. So that gives us a big class of continuous function. You can basically what you see in the textbook are all continuous. Tangent xy, tangent xyz, log of, sorry, I should use ln. So ln of x squared, e to the 2x minus sine y, all of those are continuous, all right? Okay, so to close this section, let me introduce a very nice example. This is a problem in your textbook, and I think it's also in your suggested assignment. So we want to demonstrate several properties about this strange function. So let me go through the definition first. F is defined to be 0 whenever y is less or equal to 0, so below the x-axis, or y is larger or equal to x4. So in my drawing, this red line is y equals x4. So everywhere above this red line, and also including this red line, you have the value of 0 of f. And other than these two domains, the value here and here are f of x, y being 1. Okay? So now, the first problem asks you to show that f approaches 0 whenever xy goes to the origin along any path to the point 0, 0 of a particular version, y equals mxa. So I want to emphasize that the textbook does not put this absolute value here, which you should, because you cannot define something like this when x is negative. So let me put a absolute value here to emphasize that we're taking the power of a positive number, right? Okay, so this is what I drew here. So first of all, why is that intuitively true, and why is the condition 0 strictly less than a strictly less than 4 important here? you can see that since a is strictly less than 4, so near the origin, this guy actually decays faster than the yellow line here, right? Intuitively. Because for instance, if this is x squared, then close to 0, say 0 0.1, 0 0.1 x squared is 0 0.01, right? And 0 0.1 to the power 4 is 0.0001. So whenever we're close to origin, this guy is always larger than that guy, meaning that we eventually falls above the red line, even if you might have some guy that is lower than the red line somewhere. But near origin is always larger than the red line. So that is verify that concretely. So we claim that, as I mentioned, when x is small enough, then the yellow line will always be larger than the red line. And that is very simple to solve. You see that this inequality, mxa larger than x4, can be simplified by x to the 4 minus a, which I divide here, and divide it here. So you get this guy. And since 4 minus a is larger or equal to 0, you can take the power of 1 minus 4 minus a without switching the inequality. So you get x less than m to the 1 over 4 minus a, which is not really an important number. Just means that when x is small enough, you always have this inequality. Okay? You see that when a is larger than 4, this guy is negative, so the inequality becomes reversed. But for now, a is less than 4, so we always have this inequality. When x is small enough, this guy dominates this guy. In particular, I show this for the case where x is positive. You can show that for x negative. It is quite similar. Okay, so we do verify this condition, and the yellow curve lies above the red curve when x is small enough. So when this happens, that means that the curve lies above the red curve, means that we're always dealing with the scenario here, 0. So we see that along the curve y equals to mxa, the value is always 1, 1, 1, 1, 1, 1, 1 near the origin. Sorry, it's always 0, 0, 0, 0. My bad. It's always 0. It's 1, 1, 1, 1 at some point, and 0, 0, 0, 0, 0, 0, 0. So limit is of course 0. The second part B, want you to show that f is discontinuous at the origin. So as we mentioned in the first part of this video, that even if you compute the limit for arbitrarily many different paths along the origin or any point, you still cannot conclude that it is continuous because there's infinitely many possible curves that approach the origin in this case. So for part B, what we want to show is that either along some path the limit does not exist, or along another path that the limit is non-zero, which is what we conclude in the part A. So in this case, I choose y equals to half x4. So this is a curve that is always half to the red curve, right? So it always lies below the red curve, meaning that we're dealing with this case. So you see that along this curve, we always have the limit being 1, because along that curve, you always have the value being 1. However, this guy is actually not the same as the function value 0, 0. The function value 0, 0 is 0. So first of all, obviously 1 is not 0. So the limit along this curve is actually not the same as the function value. Moreover, the limit along this curve is actually not the same as the limit along the previous curve y equals to mxa, which is 0. So not only it is not continuous, it also does not have a limit near the origin, okay? Because there are two paths with different limits. So we conclude that f is actually discontinuous. Lastly, they want you to show that f is discontinuous on two entire curves, means that this function is very, very bad. So there is a particular curve in which f jumps. And actually that is quite obvious, because we know that within this region, you have the value of 0. Within this region, you have the value of 0, right? So obviously those two curves will be the x-axis and also this parabola thingy. So let us choose, for example, y equals to 0, which is the x-axis. Now you see that intuitively, it is not continuous at this line, because when you approach x from above, when you approach the x-axis from above, you get 1. When you approach from below, you get 0. And writing down rigorously, you have whenever you're approaching a 0 for some x larger than 0, then this is 1 from above, right? Sorry, I should write, my bad. This is not correct. Y larger than 0 from above, and y less than 0 from below. From below, you get 0. So those are not the same. And similarly, for y equals x4, if you go from the exterior part, then you get the limit being 1 at the point on the curve. And if you go in the interior part, then you get the limit 0 at the point. So to be precise, when you go along the interior part, which is y larger than x4, the limit of f at the point on the curve is always 0. And if you go in the exterior part, then you always get 1. So we can always find different paths approaching the point on these two particular curves in which those two limits are not the same. So it is actually discontinuous on those two curves, which is quite intuitive because if you think of the graph of this function, it will look like this will be a level 1, level 0. And on this two different regime, you have 1 and 1. So it is a jump here and here, right? So part C actually tells us that, yeah, indeed, we have a discontinuity on those two particular curves. So I think this problem 44 is very nice in the sense that you can figure out this strange function. And you can see that even if we have a so large class of paths that has the same limit, in this case, mxa, have the same limit, but you still cannot conclude continuity. In particular, you cannot even conclude that limit exists because it actually does not exist. Right. So that's all. Let us go through what we have done in this video. So first of all, we have defined limit for multivariable function, which is actually the same in a delta epsilon sense of the single variable function. We have a natural extension of continuity, which is when the limit coincides with the function value. And we argue in 3 examples that you can, actually in 4 examples, that you can argue existence of limit either by definition, which is epsilon delta t, it is kind of hard, or you can apply the radius, the polar coordinate in a 2-dimensional case. If you want to show the non-existence of a limit or discontinuity, then you can either find a path without limit or find 2 paths with different limit. After those, we have some standard fact about arithmetic of limit, which is the same as the 1-dimensional version. You have the same continuity property. You have the same squeeze theorem. You have the same composition property, which in this case, we're composing a single variable function together with a multivariable function. Yeah, and we have this final last nice example demonstrate how we can tackle this problem in a multi-dimensional setting. Right. So that will be all for this multi-dimensional version of limiting continuity. I know there's a lot of taking because I'm not sure that you guys are familiar with the epsilon delta language. Again, let me emphasize this. This will not be of importance. I won't actually tell you to do epsilon delta proof in the quiz or exam, but this is how we quantify things as a mathematician. So we don't rely on intuition. We rely on facts and definition. So we can argue everything quantifiably. All right. So that's all. I will see you guys in the next video, which is the proof of these theorems in the sense of epsilon delta language. And then we can proceed on the next session, which is the partial differentiations. See you guys.